Hello, my name is Dorota Chańko and I study at Gdańsk University of Technology. I prepared a presentation about the generalization of Dold and Newton sequences, which is based on the project that's led by Professor Graf and Professor Gulgowski. So Dold and Newton sequences are integer valued sequences, and we will try to find their matrix generalization. But before we do that, let's talk about Mobius function. So a function mi from set of natural numbers to the set of -1, 0, and 1 is called the classical Mobius function if mi of 1 is 1, mi of n, when n is the product of k different prime numbers, is -1 to the power of k, and when n is the product of prime numbers that are taken to powers greater than 1, then it's 0. For example, mi of 30 is -1 to the power of 3, as 30 is the product of three different prime numbers, 3, 2, and 5, and mi of 4 is 0, as 4 is just 2 squared. This is the graph of Mobius function, at least for the first 11 numbers. And there is an interesting property that for n greater than 1, the sum by factors of n, mi of n over its factors, it's 0. N over its factors, it's still factors of n. And of course, it's true for n greater than 1 because mi of 1 is just 1. So another example, we take such sum by factors of 10, mi of 10 over its factors. It's mi of 10 over 1 plus mi of 10 over 2 plus mi of 10 over 5 plus mi of 10 over 10, which after summing them, it's 0. Okay, now we are ready to define Dold sequence. So an integer sequence, xn, is called Dold sequence if the following Dold congruence is fulfilled. So the sum by factors of n, mi of n over its factors times our term of the sequence, xm, must be congruent to 0 modulo n. If it's fulfilled, then xn is the Dold sequence. And of course, mi here is the classical Mobius function. So for example, constant sequences are Dold sequences because we can just take our constant term before the sum, and we know that the sum by factors of n, mi of n over its factors, it's 0. So here it's just our constant term times 0, and of course it's congruent to 0 modulo n. Another example, the sequence of powers of 2 is a Dold sequence. And also, more interesting example, if f is the function of set A to itself, and fix fn is the number of fixed points of the nth iterate of our function f, then it's all the sequence of terms that are equal to the number of fixed points of nth iterate of our function fn is the Dold sequence. Okay, now Newton sequences. So Newton sequences are also integer sequences, and an integer sequence an is called Newton sequence generated by the also integer sequence cn if an is equal to c1 a n minus 1 plus c2 a n minus 2 plus and so on plus ncn. And a1 is just c1 here. So let's take a look at the example. Let cn be the sequence 2, 0, 0, and so on. Then we can generate Newton sequence in such way that a1 is just 1 times c1, it's 2. a2 is c1 times a1 plus 2c2, so it's 2 times 2 plus 2 times 0, which is 4, and so on. Here an is c1 times an minus 1 plus c2 times an minus 2 plus and so on plus ncn, but only c1 is a non-zero number, so this is just equal to c1 times an minus 1. c1 is 2, so it's 2 to the power of n. Okay, so the sequence of powers of 2 is the Newton sequence that generated by sequence 2, 0, 0, and so on. Okay, now some interesting facts or theorems that every Dold sequence is a Newton sequence, and also the other way around, every Newton sequence is a Dold sequence. So we can say that the classes of Dold sequences and Newton sequences coincide. When it comes to integer valued sequences, they are the same for us. Dold and Newton sequences, they are the same for us. But how to generalize them to matrix sequences? We know that if they are just integer sequences, they are the same. What happens if we try to generalize them to matrix sequences? So to do that, let's take a look at posets with a function that will be assigning weights to the elements of our posets. So let P be countable partially ordered sets, poset, with partial order that looks like this. And let W be the function from our poset P to the set of integers that's assigning weights, integer weights, to each element of our poset P, and our function W must satisfy the following conditions: that for every element P of P, the set of elements that are less or equal to P is finite. For every two elements X and Y of P, if F is comparable to Y and if X is comparable to Y and it's less than Y, then the weight of X is the factor of the weight of Y, and they are not equal. And also for all weights, all natural weights K, there is at most n elements of our poset P with such weight K, and such elements are denoted K1, K2, and so on, Kn. Okay. Now let's generalize Mobius function. So a function μ star that goes from the Cartesian product of our posets with itself, so P times P, to the set of integers is called a generalized Mobius function if μ of xy is equal to 1 when x is equal to y, μ of xy is equal to the negative sum by z that are greater or equal to x but less than y, μ star of xz, if x and y are comparable and x is less than y, and it's 0 if x and y are not comparable, so otherwise. Examples now. So let P be the set of natural numbers ordered with divisibility. So here on the graph, in the graph, 1 divides everything. Okay, these are the first 6 natural numbers, of course. 1 divides all of them, 2 divides 4, and 2 divides 6, 3 divides 6, and that's it. And then, for example, μ star of 1/6 is, from definition, the negative sum by z that are greater or equal to 1 but less than 6, μ star 1z. So I just take the factors of 6 here. It's 3, 2, and 1. This is our sum. And we apply the definition again to me star 1, 3 and me star 1, 2. I take the factors of them, so the numbers that are less than them, smaller than them, when ordered with divisibility. And we are left with just me star 1, 1, which is 1 in the end. Okay, now we can define a Mobius matrix function. So Mobius matrix function M star of k arrow L is a matrix that in jth row and ith column, the term in jth row and ith column is equal to generalized Mobius function for the pair of points ki and lj, where k and l are the weights and I, j are their indices. So, for example, for posets that is a set of 1, 1, 1, 2, 2, 1, and so on. So we have 2 elements of weight 1, 1 element of weight 2, 2 elements of weight 3, 2 elements of weight 4, 1 element of weight 5, and 2 elements of weight 6. They are ordered as shown in the graph. So for example, 1, 1 is less than 3, 1, which is less than 6, 1. And the Mobius matrix function, M star 1 arrow 6, looks like this. So in the first row, in the first coordinate of generalized Mobius function is 1, 1. In the second row it's 1, 2. And in the first column the second coordinate is 6, 1. And in the second column the second coordinate is 6, 2. And after all the calculations, such matrix is equal to 1, 0, 0, 0. Now we can define matrix Dold sequence. So a matrix sequence XL, where XL, the terms XL, are matrices n by n of integer with integer terms, is called a matrix Dold sequence if for all natural L there exists such integer valued maybe matrix J, which is n by n, such that such sum is true, such equality is true. So the sum by factors of L, our Mobius matrix function k arrow L x k, where xk are the terms of our Dold sequence, it has to be equal to L, same as here, times some integer valued matrix, J. And now Newton sequence. So a matrix sequence AN, also with integers as terms, is called matrix Newton sequence that's generated by the sequence of matrices Cn, also integer terms in this matrix, which is called matrix generating sequence, if such equality is true. So AN is C1 times AN minus 1 plus C2 times AN minus 2 and so on, plus NCN. So it's very similar to the original definition of Newton sequence. Same for Dold sequence. It's very similar to the original definition of integer Dold sequence. So an example. let's take posets of natural numbers that are ordered by divisibility. And for such poset, our generalized Mobius function mi star xy is equivalent to our classical Mobius function mi of y over x. So mi star of 1, 1 is one from definition. For example, mi star of 1 and the product of k different prime numbers is equal to -1 to the power of k, which can be proven inductively. And also mi star of 1 and some number that is equal to the product of prime numbers taken to the powers greater than 1 is 0, and similarly it can be proven inductively. And so here our Mobius matrix function is a 1-by-1 matrix because we have in natural numbers we have just one term of each weight. The number n is has also weight n. So our Mobius matrix function m star x rho y is equal to just 1-by-1 matrix mi star xy, which is mi y over x. So the matrix Dold sequences behave here as integer Dold sequences, which we know that are also integer Newton sequences as their classes coincide. So is it true in general? Do the classes of matrix Dold and Newton sequences coincide in general? And the answer is no. So we can generate a sequence by a sequence of 2-by-2 matrices. Let C1 be the identity matrix and the rest of the sequence C2, C3, C4 and so on, let them be 0 matrices. So Cn generates matrix Newton sequence An in such way that A1 is C1, which is identity, A2 is C1 times A1 plus 2C2, which is identity, plus 0, which is identity, and so on. A1 is also identity. So the identity sequence is a Newton sequence generated by sequence identity 0, 0, 0. And let's take the posets 1, 1, 1, 2, 2, 1, 2, 2, ordered as shown in the graph below. So here 1, 1 is less than 2, 2, 1, 1 is less than 2, 1, 1, 2 is less than 2, 1. And is An the identity sequence, a Dold sequence for such poset n? So here's the definition of Dold sequence. If it is, then such equality must be true. But it's not, because let's take a look at Mobius matrix function 1 arrow 2. It looks like this. In the first row we have mi star 1, 1, 2, 1, mi star 1, 2, 2, 1. In the second row, mi star 1, 1, 2, 2, mi star 1, 2, 2, 2, which is, after the calculations, -1, -1, -1, 0. And mi star 2, 2 is m star 2, 2 is identity, always. M star n arrow n is always identity. So there is no such integer matrix J that this sum is equal to 2 times integer matrix J. It's not possible, because this sum is equal to 0, -1, -1, and 1. So hence the identity matrix sequence is not a matrix Dold sequence for such poset P. So it's not true in general, but we can raise the question, as Professor Gulgowski asked this question, for which posets the classes of matrix Dold and Newton sequences coincide. Thank you for your attention. The bibliography. Thank you.